Is it on?
I just turned it on. All right. So your first step, you take the vacuum. This is the bell jar. This is the plate. You're going to put your PEEP in the jar. You're going to put your plate on top. Now, you have a syringe, and one end of the syringe has nothing on it. The other end has a little white tab. That fits into the little hole in our vacuum plate. The next step we're going to do is we're going to evacuate air. When I pull the plunger out, the air is going to come from the inside of the bell jar and go into the plunger, or the syringe. And then when I push back, the air will come. It can't go this way. This is a one-way valve, so it'll go that way. Okay? And now the lid's stuck on. So now what I'm going to do is remove air, and we'll watch and see what happens with the PEEP. Okay? So this is how you put it together. When you get ready to take it apart, you just twist and pull. Okay? So once again, put the lid on, push the end of the tubing in, and begin to evacuate air. And it doesn't matter if that happens because it's a one-way valve. Okay? I don't want to spoil the surprise, so I'm not going to show you what happens. Okay, thank you. Now you can hit stop.
It is 9:46 on this Saturday morning. It is time for Imagine It. Carl Nelson's here from the Imagination Station, and you decided to bring a little color into our morning show today.
It's that time of year when you start seeing these little guys popping up everywhere, right?
I love these little guys.
Sugar, moisture, and tiny pockets of air.
Right.
So we're going to do some experiments with those tiny pockets of air.
And that's what makes them so fluffy.
Exactly,
Okay.
fluffy and light. So you can think about, I mean, inside a general PEEP, there's probably millions of tiny little air pockets.
Really?
And so
Okay.
we're not going to work with the PEEPs quite yet. We're going to hold off on that.
All
But
right.
so a balloon is kind of like one of those tiny little air pockets. Okay, and what we're going to do with the PEEPs eventually is we're going to put them inside this chamber, take the air out.
Oh, okay.
All right, so let's see what happens to a single air pocket if you do
Right.
that. So we're gonna,
So this is simulating what would be one single air pocket of all the many that you're talking about inside of here.
Exactly.
Okay.
So we turn the air pump on, and you can see the balloon will immediately start to get bigger and bigger and bigger.
All right.
So as we reduce the air pressure inside the jar, the air molecules inside the balloon are still slamming against the balloon, causing it to inflate.
Okay.
Okay? And so it gets bigger and bigger and bigger. And at some point
At
here...
some point we're going to pop. I'm getting
No,
nervous.
it's not going to pop. I don't think.
Okay.
I don't think. I think the balloon is small enough that it's going to expand, and it's pretty much going to fill nearly the entire jar.
Wow.
Now the fun part here is when you let the air back in.
Oh!
Or if it pops.
Hey, there
That
you
is
go.
cool. That is
Right.
nice. All right. So we're going to see if that's going to happen to the PEEPs themselves.
Oh.
All right.
You're going to explode my beloved peeps?
Well,
Sad. Oh, that's fun.
see, that's the fun part. All right. But we got a double whammy because the balloon actually popped there.
Nice.
So that was kind of cool.
All right.
So we're going to take our PEEPs. We're going to throw them in there.
Okay.
Get rid of our balloon. And
man.
let's add a few more on top.
It's
just
like a
for
peep
fun.
family in
It
here.
is. It's I don't know what you call a flock of peeps. Is that
A
maybe?
flock of peeps?
I don't know. I don't know what they're called. Okay. So we got the peeps in there. Let's turn the pump on. Start to remove the air. And again,
Whoa.
if you watch the peeps closely, you can see
Oh, they're starting to burst almost.
they're starting to get bigger.
Yeah.
They're starting to crack a little bit.
Right.
And kind of the neat thing here, they're getting really nice and big. That works
they
really
are.
well. Kind of the neat thing here is that the elasticity of the PEEP is going to let it get bigger and bigger and bigger.
Oh, man.
And at some point, though, they're going to start to get a little bit smaller.
Oh, I'm seeing it happening. They're
because-
starting to shrink back down.
Yeah, we've removed some of the air from inside. And of course, now, the fun part, of course, is always removing or letting the air back in. So here we go.
Oh,
And of course, the PEEPs even then get a little deflated, right?
oh look at.
As you would if you were put inside that chamber as well.
Wah-wah. Poor peeps.
So
Oh, they're not fluffy anymore.
they're not, because we've sort of ripped all those little air pockets, removed the air, and then the sugary goodness can sort of collapse back
and
down
they're
on
kind of
those.
cold.
They're a little bit cold too.
Yeah.
Yeah.
Huh.
So the PEEPs themselves, because they're sort of stretchy,
Right.
they can only get so big.
Okay.
So
But they got pretty big.
they did. That worked really well. They got pretty big. So something that would not have that elasticity of the sugary stuff would be shaving cream.
Okay.
So again, millions of tiny little air pockets inside this little thing of shaving cream.
Right. Because when you first squirt it out of the can, I mean, it's all compressed in the can and then.
Exactly. It's got all that, you know,
Right.
It's got that sound. It's putting air pockets in there.
Okay.
Let's see what happens to the shaving cream.
All right.
Same idea. We got tiny little air pockets inside there. We reduce the air pressure on the outside. Pressure on the inside is bigger.
Looks like a soft serve ice cream cone.
It does. It kind of looks like an ice cream, but it's going to get bigger and bigger and bigger. And because this doesn't have the stretchiness of the sugar with the PEEP, when we let the air back inside,
Okay.
this is my favorite part. It's kind of cool. And I don't know how much time we have to let it get big. You tell me.
We have a few more seconds.
All right.
We can let it grow a little bit here. It's getting
Because
pretty
it
big.
is much more dramatic. And again, it's just shaving cream, but there are so many tiny little air pockets. They're all expanding,
Sure.
sort of stretching the cream, making it bigger and bigger and bigger. And let's go ahead and let the air back inside
All right.
dramatically, really quickly.
Let's do it. 3, 2, 1, go. Wow. Woo.
And
Wow.
of course, and then, you know, that's what shaving cream really is.
What would a morning be without Carl Nelson making a mess in the studio, right? Oh, that's
right.
wonderful.
So
Awesome.
if the PEEPs didn't have the sugar, they would end up doing that. But
Well, there you go. Very visual. Carl, I like that. And if you want to go check out any more of Carl's segments down at the Imagination Station, don't worry. They are open today from 10 to 5 downtown. Thanks so much for coming in, Carl. 9:50. Let's go over and check in with Dave. He's got sports.
So we've put some water in the bottom of the can, and we have a nice blue cone, and we're heating the water. You should be.
You're doing a really good job.
Not yet. You gotta wait till you have steam coming out the top. Okay, can you hear boiling?
Yeah, I see the steam. Go for it.
Get it a little bit longer. Yeah, but we want a little bit more steam. All right, you ready? Go. Nicely done.
My name is Dr. Carl Ross of the University of Portsmouth in the UK. Here we have a PowerPoint presentation of a rail car tank which suffered buckling under an internal vacuum. The vessel was initially cleaned with steam internally, and it had a vent which allowed the surplus steam to be vented outwards, but it did not have a vent which allowed to release the vacuum. Unfortunately, it rained heavily, and the internal volume became under vacuum and collapsed in the method shown, which is similar to the methods of submarines collapse under external hydrostatic pressure. Mode of failure is called shell instability or lobar buckling. I have been studying this mode of failure since 1959, mostly at the University of Portsmouth.
Introducing the behavior of gases in my classroom always elicits giggles from my students. But that's okay. The idea is to keep science fun. There are a lot of demos that illustrate the gas laws, and this is one of them. This apparatus can be used to demonstrate the mathematical relations found in the combined gas law. Pressure, volume, and temperature can be measured simultaneously. Begin by opening the valve. Turn the piston so that the gasket is at a high volume. Close the valve and turn the piston to decrease the volume by at least 5 milliliters. Record the initial pressure, temperature, and volume. Turn the piston to change the volume even more. Wait a few seconds for the temperature reading to stabilize. Make sure you read the temperature before the air in the piston balances with the temperature in the room. Record the new temperature, pressure, and volume, and compare theoretical calculations to actual results. Try reversing the process. Ask students what will happen to the temperature when the volume increases. Precision lab equipment that gives students reliable results keeps science fun.